Okay, today in this video we're going to look at a very important concept of continuity. So our lesson objectives today is determine continuity at a point and continuity on an open interval, determine one-sided limits and continuity then on a closed interval, use the properties of continuity, and then understanding use the intermediate value theorem. Those are what we're going to be focused on. Now, at this point in time, you have a very basic understanding of continuity. Generally, if I asked you what it meant for a function to be continuous, you would tell me that it means that it's something I can draw without picking up my pencil. So, we're going to build on that right now. Let's start by looking at the definition of continuity at a point, at a particular point x equals c. Okay. What I'd like you to do is pause the video for a minute, and I want you to think about things, what you think must be true in order for me to say function is continuous at a particular x value. So pause the video, think about that, see what you come up with. Okay, welcome back. In order for a function to be continuous at x equals c, there are three conditions that actually must be met. Okay, so the first one of those, number one, f of c must exist. When I plug whatever c is into the function, I have to be able to get a number. It can't be something that's undefined. So that's the first one. Number two, the limit as x approaches c of f of x must exist. A function cannot be continuous at x equals c if its limit as x approaches c does not exist. Okay, so you have to be approaching the same values from the left and from the right. Now, a lot of people think, wait a second, isn't that enough for me to say that a function is continuous at x equals c? And actually, no, it's not. There is a third condition that must be met. We're making an assumption on here. When we think that this is sufficient, we're making an assumption that we can't necessarily is true, and you'll see that in a second. The third condition that must be true in order for a limit to exist, or for a function to be continuous at x equals c, is that the limit as x approaches c of f of x must equal f of c. If those three things are not true, or we cannot say that they're true, we cannot say that a function is continuous at x equals c. Now, the next thing that we have as well with this is continuity on an interval. Okay, a function is continuous on an interval if it is continuous at every point in that interval. A function is continuous on an interval from a to b if it is continuous for every number c which is in that interval from a to b. For every number c which is an element of the interval from a to b. Now, to get a look at what continuity means, let's take a look at what it means to not be continuous at x equals c. What happens if those conditions are not met? What you see on this one here, we have some graphs that are not continuous at x equals c. In the first graph, in this first one here, what we have is that we have a function where we have a hole at c. We have what's called a removable discontinuity at c. So in that case, this function is not continuous because f of c does not exist. In other words, and think about it, if you could not draw this graph without picking up your pencil because we have a hole there. Okay. In the second graph, this one here, What we have is a function that as I come from the left and come from the right, I approach different values. I'm not approaching the same value. F of c does exist, and I know that because right here we do have a closed dot. So I know at that point that's the value for c, for f, when we plug c in. So it does exist. The problem is that the limit does not exist. As I come from the left and as I come from the right, I'm approaching two different values. So the limit in this case does not exist. What we have in the third graph is the one that really kind of goes and illustrates this, why that third piece is important. Remember, in math, when we look at a lot of these theorems and so forth, we are going to be looking at making sure that every possible, we want to have something that will be true for every possible thing that could be weird. And that's what we're looking at here. In this case, I have a function. It is defined at x equals c. The value, that closed dot right there, tells me what f of c is, whatever that value is. The limit exists for f of x as x approaches c. As I move closer and closer to c, from both directions, I'm approaching the same value. But the problem is I'm not approaching what f of c is. So in this case, this function is not continuous. And that is why this third piece, that third piece is so important. It doesn't matter if you think it's something that's realistic or not. The fact that I could go through and draw something that would still be a function where the limit exists and f of c exists, but it's not continuous, is the point on this one. And you have to go through and look for every possible way that something could be strange. Now let's look at what it means to have a one-sided limit. When we look at one-sided limits, what it means is that we are going to be approaching from one direction and one direction only. So when I go through and work with that, I have to be sure there has to be some notation to indicate that I am dealing with a one-sided limit. And what we'll use is either a small plus or minus sign as looking like an exponent on what x is approaching. For example, if I want to find the limit as x approaches c from the right, what I will write is I will say I want the limit as x approaches c from the right. That little plus sign means from the right of f of x. And then I will just go and look at the function, try to determine as I move closer and closer to c from the right. So I'm looking at numbers that I'm starting out bigger than c and I'm moving towards c. As I do that, I'm asking myself, does this approach a particular value? Okay, does it approach one particular number? If so, then I would say that that limit was equal to whatever that number was. We'll say L. If I'm going to have a one-sided limit and I'm going to be looking at when it approaches x from the left, as x approaches c from the left, what I will have is the limit as x approaches c from the left, that's the minus sign, of f of x. Okay, and so what I'm going to be doing is I'm looking at numbers in this case that are smaller than c, whatever c is, and I am going to go and move closer and closer to c, try to determine what is happening there. And and then I will go and say, if it's approaching a particular number, then I will sit there and say what it's equal to. And it could be equal to, let's go L sub 1. Okay. And what happens, and really what comes down to this is that in order for the limit of a function to exist, that limit will only exist if and only if the limit as x approaches c from the left and the limit as x approaches c from the right are equal to the same number. In order for that limit to exist, the two values that I'm approaching as I come from the left and from the right must be equal. Think of it this way. Basically, in order for the limit to exist, if you trace from the left and from the right, if you trace the graph with your fingers should come together at C. If they don't come together at C, the limit doesn't exist. Now you'll notice I just drew a graph there of a function, f of x. That function is in red, and we have C is labeled on the x-axis. And what I would like you to do, I would like you to identify the limit as x approaches C from the left and the limit as x approaches C from the right of that particular function. So pause the video, identify what those are. What the limit as x approaches C from the left and what the limit is as x approaches C from the right. Okay, welcome back. What I want you to recognize on this one, that the limit as x approaches C from the left, in this case, is going to be 7. As I come from the left, remember I'm using numbers that are smaller than C. As I come from the left, that means I'm looking at x values over on this side, which corresponds to this piece right here. So as I move towards C, as my x values move in this direction towards C, my function values are coming down and they keep getting closer and closer to this particular value, 7. The limit as x approaches C from the right, in this case, is as I come from the right, I'm using numbers that are bigger than C. It's going to correspond to this portion of the graph. And as I move towards C from the right, my function values are getting closer and closer to 5. So in this case, the limit as x approaches C from the right is 5. This now does conclude the video for section 1.4 on continuity. And with that, I will see you in our next class. Now let's look at a different example. In this case, what we have is we have a piecewise function. F of x is equal to 3x cubed when x is less than or equal to 1. And it's equal to a linear function ax plus 5 when x is greater than 1. And what we want to do in this case is we want to find a value for a, in this case, such that f of x will be a continuous function over the, in this case, the entire real numbers. We know, in this case, I know that 3x cubed is continuous over its domain. So for every value of x that's less than or equal to 1, I know this is continuous. This is a linear part. The second part is a linear function. A linear function is also continuous. So I know that this, no matter what a is going to be continuous when x is greater than 1. So the only issue I have is really what's happening at x equals 1. And so what I have to do is make sure that the definition of continuity is satisfied. Well, remember, in terms of continuity, the first part is f of 1 must exist. And in this case, f of 1 does exist because I know that this top piece is x is less than or equal to 1. So 1 is plugged into this top piece, and I get that f of 1 is equal to 3. Now the other part is the part that's going to help us out the most. We know that the limit must exist. So in other words, in order to be continuous, the limit as x approaches 1 from the left of f of x must equal the limit as x approaches 1 from the right of f of x. Well, in this case, to find the limit as x approaches 1 from the left and from the right, all I need to do is plug 1 into each piece. That's what some of the properties we saw before with limit properties allowed us to do, that we can just plug that in. And so the limit as x approaches 1 from the right, in this case, is 3. And the limit as x approaches 1 the limit as x approaches 1 from the left is 3. And the limit as x approaches 1 from the right is going to be a plus 5. I just put 1 in for x. A times 1 is a. And now at this point, I will solve for a. To do that, I just subtract 5. And so I get negative 2 equals a. So if a equals -2, f of x is continuous at x equal to 1. You might be saying, well, wait, what about that third condition? We didn't talk about that in this one. Well, in a way, we don't have to because of the fact that right here, this part right here, by saying that the limits from the left and from the right are equal, I'm forcing the limit from the right to equal the limit from the left, and the limit from the left is also equal to the function's value. So by doing this piece right here, I'm forcing that third condition of continuity to be true. Now, let's look at some properties of continuity. Okay, first of all, if I let f of x and g of x be continuous functions at x equals c, then the following are going to also be continuous at x equals c. F plus g and f minus g, as well as f times g, will be continuous at x equals c. I won't have any problem there since f and g are already continuous. I'm just taking a number, basically in all three of these, those two and that one, I'm just taking two numbers, I'm either adding, subtracting, or multiplying them. Okay. The other one is that at the division, f divided by g is continuous at x equals c, provided that g of c does not equal 0. Obviously, if g of c equals 0, then I'm going to have a division by 0, which is undefined, so therefore the function, that resulting rational function, won't be continuous. The other one I have is that if I take a constant times a function f, where that constant is some real number, then that result will also be continuous at x equals c. So those conditions right there, along with this, we know there are a series of functions that we already know that are continuous at every point in their domain. So what we have right now is that we know polynomials. Any polynomial is continuous at every point in its domain. In fact, it's a polynomial, the domain is the real number. So this is continuous for every real number. Another one that we have are rational functions. Rational functions are continuous for every point in its domain. Rational functions are the ones that are p of x over q of x. And the domain of this is all x, provided that q of x does not equal 0. So therefore, the values that make q equal to 0 are already being excluded from the domain. This thing is continuous everywhere else. Okay. Radical functions are also continuous at every value of x in the domain. Okay. These are where we're dealing with any nth root of x. Okay, so obviously when we have we've talked about this last year, when n is an odd value, then it's all real numbers in this case. When n is even, then we're going to be dealing with where the domain is going to be x greater than or equal to 0, but that will be the domain, those will be the domains. And the other one that is continuous at every point in its domain, the ones that you will probably recall a lot, that we dealt with last year a lot, are the trig functions. Sine, cosine are continuous for every real number. And then the tangent, cotangent, secant, cosecant, obviously those ones have vertical asymptotes, so they are continuous at every point between the vertical asymptotes. These facts, in terms of these four types of functions, along with the properties of continuity, really go through and extend your ability to tell me different functions are continuous to a lot of different ones. Any combination of these, where I have a radical plus a trig function, or trig plus a rational, those would all be, we could all say those are continuous over their domain. Now let's look at a very important theorem. It's called the intermediate value theorem. If f is continuous on a closed interval from a to b, and f of a does not equal f of b, and k is going to be some number between f of a and f of b, then there is at least one number c in the closed interval from A to B such that f of c is equal to k. There's a lot of words here. I've drawn a picture that hopefully will help clear this up. I have a function in black, f of x. We have values at A and B that are, and I can go up from A, that's this red line. I get to this point and I can say f of A is whatever that value is. Same thing for B. I go up from B, that red line, come across this blue line, and I know that f of B is there. Now, if f is continuous, what that means is that if I pick any value between these two, so I pick k, then there's at least one point where I can come over and I can hit the curve, from k, I can hit the curve and drop down somewhere between A and B. In this case, for this k, I have 3 spots. Notice if I came over here at this one, I would come over, hit the curve right there, and I'm definitely going to drop. I'm going to drop very close to A, but it does work out. Okay. If I pick some value here, I can come here, hit the curve, and drop down. Maybe I hit the minimum there. Okay. So in this case, this is what the intermediate value theorem says, that if I pick any value in here, because the function's continuous, I can come across, hit it at some point, and fall between these values. The intermediate value theorem is what's called an existence theorem. It tells me something exists. It doesn't tell me how often it happens. In this case, k intercepted the, there were 3 values that I could use, that I could plug into f and get k. But that doesn't necessarily have to be the case. There might be 1, there could be 10, there could be whatever number. But what the intermediate value theorem says is that there will be at least one number as long as the conditions that we have up here, that f of x is continuous on that closed interval and f of a does not equal f of b. There will be at least one number. It will happen at least once. Let's now look at an example, and really this example uses the intermediate value theorem. We want to explain why the function f of x, which equals x cubed plus 5x minus 3, must have a 0 in the interval from 0 to 1. In other words, graphically, this function must cross the x-axis at least one time, somewhere between 0 and 1. So what I'd like you to do, think about what the intermediate value theorem says. Also, think about what it means for a function to have a 0, what that means, and what it means to cross the x-axis. And I'd like you to go through and come up with your explanation on why this function must cross somewhere between 0 and 1. So pause the video, come up with your explanation, and then once you're set, come back and we'll go through the solution on this one. Okay, welcome back. In this case, to go through with the intermediate value theorem on this closed interval, what I need to do is I need to find we have our closed interval is the interval from 0 to 1. So what I need is I need to know f of 0. In this case, f of 0 is equal to 0 cubed plus 5 times 0 minus 3. And that result will be negative 3. So I know f of 0 equals negative 3. The next one I have to do is find f of 1. F of 1 is equal to 1 cubed plus 5 times 1 minus 3, which in this case is going to be 1 plus 5 minus 3, and I know that's equal to a positive 3. So I know in this case f of 1 is equal to positive 3. The other thing I know is that f of x is a polynomial, so therefore it is continuous over its domain, for all real numbers. Okay, so then by the intermediate value theorem, I know that f of x is continuous. This is continuous. I know that f of 0 is negative 3 and f of 1 is equal to 3. And so by the intermediate value theorem, for every value between negative 3 and 3, I know that there is a number between 0 and 1 that when I plug it into function f, I will get that value. Well, in this case, 0 is between negative 3 and 3. And since when we talk about a 0, that's where we're crossing the x-axis, that means that the function's value is 0. So by the intermediate value theorem, I know the function must cross the x-axis somewhere between 0 and 1.